and this piece are all identical, and the entire piece goes to 0, the answer is always 1. If any of these is not the same, is different, and this does not go to 0, the answer is not 1. So I want to give an example. Here's limit of sine x minus 1 divided by x squared plus x minus 2 when x approaches 1. And normally you will say, what is this? What are you talking about? How is this connected to that? I don't see it. And then I would have to say, you're right. At this stage, it does not seem to be connected. These do not seem to be connected. But here is what I need to do first, like always. Plug in 1. 1 minus 1 is 0, sine of 0 is 0. Plug in 1, 2 minus 2 is 0. So there is hope. My next step, of course, will be to factor the denominator. Can anyone tell us the factor form of the denominator?
X minus 1, x minus 2.
X plus 2, x minus 1. Good. So this is the limit as x approaches 1 from sine x minus 1 over x plus 2 times x minus 1. I'm going to use my props and ask you, as x approaches 1, where does this go?
3.
Excellent. Keep that in mind, but I'm not really interested in that piece. I'm interested in those pieces more. I hope you agree that I showed so far that this piece has the same thing in the denominator. Agreed? Yes? Do I get anyone to agree with me?
Yes.
Okay, perfect. But we do have one more piece to make sure it works. Would you accept that when x approaches 1 and I move 1 to the other side, or subtract 1 from both sides, this is the same thing? If x approaches 1, is like saying that x minus 1 approaches 0?
Yes.
Perfect. So I do have all three pieces the same. I have this, I have this, I have this. And it approaches 0. So without looking at what I covered with my prop, what do you think this limit would be without that?
1.
Exactly. But now I have to be careful, because I also have a 3 in the denominator this time. So what is the limit?
1 over 3.
That's it. Because I was able to show all these three pieces being identical and this approaching 0. This piece is just sand in my eyes, right? Just to throw me off. But actually the limit is 1/3. Great job. So now, again, because I don't want to wait till chapter 4, this is so important and so useful that I don't want to wait till chapter 4. This is called L'Hôpital's. It's written with a tréma here, it's in French. So L'Hôpital's rule. That's his name. Okay, so what did he say? He said that only in a limit, we are only talking about a limit, as x approaches a from a ratio, and only in two situations. if you remember, we talked about 3 indeterminate cases. We talked about this, we had examples. We talked about this, we had examples. And we talked about this, we had examples. But only in these 2 situations, L'Hopital's rule is applicable. So only if I apply a limit to a function that is a ratio, and I get 0 over 0, or infinity over infinity, then I can do this that I can never do otherwise, only inside the limit. So if that's the case, then the answer would be, so the limit as x approaches a from p of x over q of x will equal, only if we have these 2 situations, p prime, a limit, of course, x approaches a from p prime of x over q prime of x. This is unheard of. I'm not differentiating the quotient. This is wrong. If I ever differentiate a quotient like this, I can never get anything. But only inside the limit, and only when it's a quotient that reduces to 0 over 0 or infinity over infinity, I'm allowed to continue with the limit as x approaches 0 from p of x over q of x. P prime of x over q prime of x. So this is when x approaches a. Oh, of course, it will take a moment. So when x approaches a. So only then this is allowed, and the answer will be the same. Coming back to our example, I want to determine limit as x approaches 0 from sine x over x, although we know the answer. I plug in 0, the top is 0. I plug in 0, the bottom is 0. It's a quotient. It's inside a limit. I would write limit as x approaches 0. I differentiate the top, which now I know is cosine x. I differentiate the bottom, which now I know is 1. And what is the answer?
Is it 1?
Very good, because cosine 0 is 1. And that's our proof. Okay, let's look at another limit. As theta approaches 0. Any questions? I'm sorry. Any questions? So this is a limit as theta approaches 0 from sine theta over theta plus tangent theta. I'm asked to find the limit. I have to do the first thing that needs to be done. I have to plug in 0, and I get 0 over 0. Yay! I like it. Because L'Hopital's rule says that if I have to find the limit of a ratio and I get one of these 2, I can simply differentiate the top. I'm not applying the quotient rule. I will never do this to a function, ever. But it's inside a limit, and I'm allowed to. Sine prime, cosine theta, theta prime, 1, plus tangent prime, secant squared. Now I have to plug in again to see what's next. I'm not going to continue differentiating unless it's 0 over 0. I can differentiate again if it's 0 over 0 or infinity over infinity. So where does this go when theta approaches 0?
1.
Very good. Where does the denominator go when theta approaches 0? Remember, secant squared is 1 over cosine squared.
So 2?
Exactly. And it's done. Any questions? Any questions? Now, at this point in time, a problem like the next one, we will not be able to use this rule yet on such a problem. You will see why in the next section. So let's say limit of sine 4x over sine 6x when x approaches 0. And I'll promise to stop after this one. Yes, I plug in 0. Yes, is 0 over 0, but there is something we don't know yet that we have to wait till Monday. Okay, so one comment I have here. We will commit to memory that limit as x approaches 0 from sine x over x is 1, but also limit as x approaches 0 from x over sine x is also 1. If you differentiate, the numerator is 1, the denominator is cosine, so it's also 1. So sine x over x or x over sine x both give us 1 as long as x approaches 0. I need this idea here. So now I can differentiate because this is a function of a function. So this is f of g of x, and we do not know how to differentiate that till the next section in 3.4 when we use the chain rule. That's why I cannot show that with the chain rule right now. Okay, so then I continue here, and I'm going to try to manipulate a little bit the function. So would you agree that when x approaches 0 and multiply both sides by 4 or multiply both sides by 6, I still get 0? If x approaches 0, do you agree that 4x approaches 0 or 6x approaches 0? Is it a yes? Is it a no?
Yes.
Perfect. Why do I need this? For these two quantities. If I were to use this important result, then I have to have this and I have to have this both going to 0. Now, I'm going to manipulate this function in this way. If I multiply the numerator by 4x and the denominator by 4x, do I change the function?
No.
No. So then I have sine 6x, and then I multiply the numerator by 6x and the denominator by 6x. If I multiply the numerator by 6x and the denominator by 6x, do I change the function? No, this is 1 and this is 1. I didn't change the function. This is 1 and this is 1. However, knowing the result, I know that all this, because 4x approaches 0, will approach what? All this.
1.
1. Great job. Now I have this. And then I know that all this, when 6x approaches 0, will also approach
1.
Excellent. Look what is left. Careful. This is left, and this is left. but I will simplify by x. 1 and 1. So therefore, what is the final answer?
1. 2/3.
4 divided by 6. Excellent. 4 divided by 6, which is indeed 2/3. How did I manipulate this function? I multiplied by 4x because I needed it, and multiplied both top and bottom. How did I manipulate for 6x? I had to multiply top and bottom by 6x, but this is nothing, it's 1. This is nothing, is 1. It's still the same function. But this approaches 1, this approaches 1, and then 4x over 6x is 4 over 6.